Hey, this is Professor Dan Kernler again, and this video is part of our Calc 3 sequence. In this one, we're looking at section 16.5, where we are doing triple integrals again. Yes, triple, but this time we're doing something called cylindrical and spherical coordinates. So think of these as like the three-dimensional versions of polar. One of them actually ties in really directly, and then one of them is a little bit different. In this first video, we're going to focus on the geometry of it. No calculus, just the geometry of these two coordinate systems, cylindrical and spherical coordinates. First, quick refresher for polar coordinates. If we have a point out here and its coordinates, say, are x, y, we can also define that point by a distance r from the origin and an angle theta from the positive x-axis. And so then we have this relationship between the rectangular coordinates and their polar coordinates. So what are cylindrical coordinates then? Well, all it is you have in the xy plane, you have your point here, and there's some distance r. The point is in the xy plane, point is in the xy plane. You have your distance r from the origin and the angle theta from the positive x-axis. And then what if you just go up a certain z amount? And so you have r theta z. And that is what the cylindrical coordinates are. All they are is just essentially adding the same z coordinate that you would to the rectangular coordinates to the polar coordinates. So let's talk about how to convert these. If we're going to convert between the two systems, between cylindrical and rectangular, we're really just dealing with the x and y versus the r and theta. So let's graph this one here. We have 3, 7 pi over 4. I'm just going to focus on x, y, and r theta. So 7 pi over 4 is down here, a distance of 3. Let me label that here 3, and this is 7 pi over 4. And so x would be our cosine 7 pi over 4. And then y would be our sine of 7 pi over 4. The cosine is positive here, but the sine is negative. And so then our point would be 3 square root of 2 over 2, negative 3 square root of 2 over 2, and then the z stays 4. And that's all it is. The only difference there between rectangular and polar is the x and y, or the r and theta. The z is equivalent between the two. Vice versa here, what if we have the x, y, z, and we want to convert those to cylindrical? Well, let's just graph our point, 4, negative 3. So we're over here actually in the same quadrant. We need to figure out the r. Well, x squared plus y squared equals z squared. Oops, wrong one there. 4 squared plus negative 3 squared. I don't know if you recognize that one. Actually, not z squared. What am I talking about? R squared. That one is 3, 4, 5 Pythagorean triple. And then we'll have to use tangent. Tangent theta, let's see, will be equal to opposite over adjacent. So we have to be careful here. We want to go arctangent of negative 3/4. But we have to be careful. Is theta equal to that? We have to think of the range of arctangent. And if you recall, that was between negative pi over 2 and pi over 2. And so that should be fine here. Theta will be, that'll actually give us, what it'll give us here is, it will give us the theta here. It'll give us a negative angle, which is fine. Theta does not need to be positive or negative. There are multiple angles that are coterminal that will give you that. So in cylindrical coordinates, this would be 5 arctangent of negative 3/4, and then 1 is still the z. Okay, let's talk about some graphs. What would the graph of theta equal pi over 3 be? Now, keep in mind, this is in cylindrical coordinates, not polar. So this is in 3 dimensions. You have to think about x, y, z, and you're at an angle of pi over 3 from the positive x-axis, but there's no restriction on z. So what you really have here is a plane, right? It's a plane, a vertical plane through the angle theta equals pi over 3. What would the graph of z equal 4 be? I mean, that's just what it is, right? That's just what it is in rectangular coordinates. It's a plane parallel to the xy plane at z equal 4. All right, and lastly, some of the benefits of cylindrical coordinates. Let's look at this graph to the right. You can see we have a cylinder. If we zoom in, it gives us here, it's centered at the origin and the radius is 3. So in rectangular coordinates, that would be x squared plus y squared is equal to 9, and then z is free, so that gives you z moves up and down. For cylindrical coordinates, that's just saying r is equal to 3. So those are cylindrical coordinates. Let's talk a little bit about some additional equations here. What would the surface r squared equals z squared plus 1 create? Let's think about that. R squared equals z squared plus 1. Well, r squared is x squared plus y squared equals z squared plus 1. And if we subtract x squared plus y squared minus z squared equals 1, you might recognize that, you might not. Let's do some traces. So the xy trace when z is 0, that's a circle, x squared plus y squared equals 1. Let's do the xz trace when y is 0. That's x squared minus z squared equals 1. That's a hyperbola. And then the yz trace, when x is 0, also that same hyperbola. So this one is a hyperboloid, x, y, z, and it's hyperbolas here, and it's a circle in the xy plane, and then a hyperbola over here. Whoops, that is not good. All right. I don't know if you can kind of see that. That's a hyperboloid. That's what that one is. Let's see. Z equals x squared over 9 plus y squared over 9 is a circular paraboloid. Notice if x is 0, you get a parabola, and if y is 0, you get a parabola, and then if z is 0, actually you just get the origin, so it's a paraboloid. It looks like this. That's like a terrible paraboloid. We can do this here. Draw some concentric circles. Something like that. All right. So what would its equation be in cylindrical coordinates? Well, we know x squared plus y squared is equal to r squared. So I guess we could divide both sides by 9. X squared over 9 plus y squared over 9 equals r squared over 9. So that means z is equal to r squared over 9, or r squared equals 9z. And that would be the equation in cylindrical coordinates. Okay, cylindrical, not too bad. Just has the z extension to polar. Let's talk about spherical coordinates. Now you might guess that spherical coordinates are going to be helpful if we're integrating over a spherical region, and that is exactly correct. Just like in polar coordinates, essentially everything was circular. So if we're integrating over a circular region, polar coordinates were the way to go. So here's how spherical coordinates work. We have some point out here in space, and it's defined by 3 quantities: the distance from the origin, and then if we project it down to the xy plane, there is an angle theta from the positive x-axis, and then there is an angle phi from the positive z-axis. That's phi. So the relationship here with rectangular coordinates is where there's still a vertical z. Somehow we'll have to figure out how that's connected. And then there's this r, which is the connection to the polar coordinates. The r is the the distance kind of below it here, this is in the plane x, y, or r theta. So the theta is the same as for cylindrical or polar. The rho is the distance from the origin directly to the point, and then the phi is the angle from the positive z-axis. And phi will always be positive, non-negative angle, and it's less than or equal to pi. So you're not going to swing all the way around. It would be positive, but then on the other side. Let's talk about relationships between the systems. So rectangular and spherical coordinates, relating the two. So first, let's talk about relating r to rho and phi, and then use our relationship with r in polar coordinates to get the x and y. So if we think about that picture there, I want to look at, let me go back up to the previous one here. I want to look at this right triangle right here. I want to look at that right triangle. So it had r, what was in the xy plane, the height was z, and then this was the side rho. The angle phi was here on this side, and using our geometry, we know the opposite, or the alternate interior angle is also phi. If I can write a phi, something like that. Okay, so let's take a look here. We know, let's see, this is a right angle. Sine of phi, sine would be opposite over hypotenuse. So that means r is rho sine phi. But we already know x is r cosine theta, so x must be rho sine phi cosine theta. And we know y is r sine theta, so that must be rho sine phi sine theta. So given the rho and theta and phi, that's how we can figure out x and y. And then, let's see, I guess we could do the z a variety of ways. We know that r squared plus z squared is definitely equal to rho squared. Let's see here. Then we could do z. Let's see, where's my z? I need to get my angle. I need to get z from phi and rho and theta. Let's see, z will be cosine. Cosine phi equals z over rho. So z is equal to rho cosine phi. So let's go down below. Oh, I'm getting ahead of myself here. That's what I was doing here. Cosine phi equals z over rho. I knew it was like a place to do that here. And z is rho cosine phi. So down below, we have x is equal to rho sine phi cosine theta, and y is equal to rho sine phi sine theta, and z is equal to rho cosine theta. Cosine phi, I should say. X squared plus y squared plus z squared is r squared. And then tangent theta, that's in the xy plane, that will still be y over x. And then for phi, you can do, we'll kind of leave that for you to investigate. You can do that similarly. You can do a little substitution there and solve for the arc cosine of phi by using that right triangle that is in that same right triangle there. Okay. All right, I think that's it for that. Let's finish by talking about some graphs of spherical equations. First one here, rho is equal to 5. If rho is equal to 5, we're going to try to draw a picture or describe in words. So think about these. Maybe pause the video for each one as we go. Maybe pause it right now. Actually, that'd be great. Why don't you pause it right now and take about 5 or 10 minutes and see if you can do a quick kind of sketch for yourself, or maybe write down what you think these each are. Okay, so hopefully you had a chance to do them. I think this would be better to do it. If you haven't, if you're just kind of hoping like, well, he'll give us the answer, I do think it would be good for you to go back and do these, but I'll talk about them right now. If rho is equal to 5, that means phi can be anything, theta can be anything, rho is just always 5. Well, that's a sphere, radius 5, centered at the origin. Theta equal pi over 4. Theta equal pi over 4. Whoops, went too far. Theta equal pi over 4 is going to be the same thing to the one we did before, where it was a fixed angle. So theta is the angle from the positive x-axis. I think I went too far there. Something like that. Pi over 4. And there's no restriction on r, so you're going in and out however far you want. And there's no restriction on phi, so you're rotating from the positive z-axis as far as you want. So you are, again, that's terrible. You're a plane. I am just not drawing well tonight. Look at that. We're a plane through the z-axis at an angle of pi over 4. Now this is different here. Phi is pi over 4. This one is a cool one. So phi is the angle from the positive z-axis down. So you're at an angle of pi over 4, but theta is not limited. Theta is not limited. And rho is not limited. So what you end up with here is a cone. So you are pi over 4 down, but you're all the way around pi over 4. Oh, and we should clarify here, we go back up to the definition for rho. Rho here is the positive length of the line segment. So we're just going to be the top half here. If we wanted the bottom half, we would have to say that theta could be 3 pi over 4, would give us the bottom half. It has to be a positive rho. All right, last one. Rho equals phi. This one I should have my maple up. We can pull that out if you like. If you kind of just look from the side, pick one of the axes here, x or y, and then you have z. So when you are right on the z-axis, phi is 0, so rho is 0. As your angle increases, your rho also increases. And so when the angle is pi over 4, you're at a distance of pi over 4. When the angle is pi over 2, you're at a distance of pi over 2. When the angle is 3 pi over 4, you're at a distance of 3 pi over 4. When the angle is pi, you're at a distance of pi. So it makes this cool curve, kind of like a heart. But then, what does that say about theta? Well, there's no restriction on theta, and so it spins around. So I have no idea how to draw this. But it's this, and then spun around in 3 dimensions, right? That's kind of plausible. I don't know. Maybe. Yeah. Wow, that actually looked better than I thought it was going to. So the z-axis is right down the middle. The x-axis comes right out through this, and then the y-axis out the other side. Now let me see if I can get a maple version of that. I have one open here. Okay, so I have a little exploration here. We're looking at positive x-axis, positive y-axis, and as I sweep out, we're just going to do just in the xz plane here. As I sweep out the rho equal phi just in the xy plane, we get that curve. And then as we let theta vary, oh, pretty. So it looks pretty cool, kind of like a little top. I will say that that is a really good picture. That's not bad. Okay, that is it for this video. No calculus in this one, just some geometry. In the next couple of videos, we'll do talk about what integration looks like in cylindrical and spherical coordinates, especially spherical. That's actually where it's most interesting. And then we'll do some additional examples in the third video.